In this video, we'll be investigating a situation involving moving charges using the concept of conservation of energy. Just as in mechanics, energy conservation can give a very efficient way of finding things like velocities and positions without having to worry about forces, without having to worry about vectors or calculus or kinematics, any of that. Though the answer will be the same as if you had done it using kinematics and forces, it'll be much more efficient. So whenever you can use energy conservation, it's best to do so. Let's take a look at the problem statement. So in this problem, we have two fixed charges and then one particle that can move. The fixed charges are at plus and minus x equals 3. And then we have a moving charge that currently is at y equals 4 on the y-axis. And that particle, from what it tells us, is that it's moving downward, and we're asked to find its velocity when it gets to the origin. What we know is we know the charges of all the particles. We know that the kinetic energy when the moving particle is at the point 0, 4 is 1.2 joules. And then we're looking for the velocity here. So what we're going to do is we're going to use energy considerations to find out what the velocity is. Now the thing about energy considerations and energy conservation is that sometimes you lose the intuition because you're not drawing any vectors or dealing with the forces. So before we go through the mathematics for that, I want to first just get an intuition about why this particle is actually moving downward by drawing the forces on that particle. So actually, why don't you go and do that on your own, determine the forces upon this moving charge based on the other two charges, and then from that determine the net force, and we'll come back and take a look. So to find the force on the negatively charged particle that's right here, we can just kind of look at the forces that are exerted on it by the fixed positive charges. And I'm just going to draw it down here so that it's not cluttering this diagram. We have the negatively charged particle right here, and it's going to feel a force that's attractive between these two because they're opposite charges. So this positively charged particle, which is fixed in place, will exert a force pointing downward and to the right upon this negatively charged particle. So it's going to feel a force down like that. And then I'll just say that's from the particle at x equals positive 3. And then likewise, we're going to have an attractive force between these two particles. This one's fixed in place. It's going to exert a force upon this guy downward and to the left because those are, again, attractive. And so that's going to be a force kind of in that direction. And that's due to the particle at x equals negative 3, so I'm just going to put a negative there. And these, of course, are going to be equivalent in magnitude because they have the same charge, the same distance away, so the forces will be equal. And so I drew vectors of approximately the same size. Now if I add these two vectors together, I can just move this vector down here and add it head to toe as you always add vectors. And so if I put F minus down there, we get a net force that indeed does point down in the negative y direction. So that indicates to us that if this particle is already moving in this direction, as the problem says, then the force is going to be pulling it down so that it'll accelerate in this direction. In other words, because it feels a force downward, it's going to accelerate downward, which means that its speed is going to change. And so we know that at some point this particle is going to be down here at the origin. And because its speed is increasing, we know that the kinetic energy has to change, and kinetic energy is going to be higher when it gets to the origin. So when we do find the kinetic energy at that point, we can always test it back with our intuition and say, has a particle actually sped up as we expect it to? In any case, that's a little bit of the intuition of what's going on here. This particle is moving downward because the net force on it is downward. And then we're going to be looking for the velocity when it gets to the origin here. The approach will be not to use forces, though, but to use energy conservation. And so first, whenever you use energy conservation, you always have to ask yourself, is energy conserved in the first place? And in other words, now, first of all, the total energy is always conserved. But you don't want to have to deal with things like frictional forces and dissipative losses because those are hard to quantify sometimes. So in situations where you don't have dissipative losses or frictional forces, the mechanical energy is conserved. In other words, a kinetic plus a potential energy is conserved. And what that means is that it's the same at every given time. Is that the case here? Well, we're never told that there's any dissipative losses, so though friction may exist, we can assume it's negligible and not relevant for the problem, which means that the mechanical energy is conserved. And so we have that the mechanical energy, which I'll call E, and it's going to be the sum of the potential and the kinetic energy. I always use T for kinetic energy and then U for potential energy. That quantity, the sum of those two values, is conserved, meaning that at any point along the particle's trajectory, this value will be the same. So if we know the energy when it's at 0, 4 right over here, and we get a value, let's say it's 5 joules or something, once it gets down to the origin, that value of 5 joules will be the same. The only thing that may change is that its distribution between kinetic and potential may change. So the approach here is this. we're going to use the fact that we know the kinetic energy when it's right there, and we can find the potential energy by considering the presence of the other charges. So we're going to use that to find the total energy at 0, 4. So find the energy when it's at the original point by adding up the potential and kinetic energies there. Now that we have that value, it's fixed. So when it gets down to the origin, that value will still be the same. And we're going to use that one to find the kinetic energy at the origin. And the way we can do that is by subtracting out the new potential energy there, which we can find using the configuration as well. And then finally, once we have the kinetic energy at the origin, we can just use the formula for kinetic energy, which is 1/2 mv squared, to find the velocity. So we'll use t to find the velocity at the origin. Okay, so the first step here is to find the total energy. And as a reminder, the electric potential energy is given by the following formula. It depends on the Coulomb constant, and then you have the product of the charges. So far it looks very similar to the force formula. They're dividing by the distance between the charges, but it's not squared this time, it's to the first power. And so there's a couple of distinctions here between the formula for the energy and the formula for the force, the Coulomb force. The first is that you have only a scalar quantity here, so there's no vectors or components, it's only a single number. And the second is that in the denominator you have r to the first power, not to the second power. So now that we have a formula for the electric potential energy, you can use this to find the total potential energy of this particle by taking the potential energy it has between these two charges and these two charges. Once you get that potential energy, add it to the kinetic to find the total energy, and then from there we'll proceed. So take a minute and do that now. The potential energy of this particle when it's at 0, 4 is going to be due to two different charges. First, it's going to have potential energy due to this one, and then it's going to have potential energy due to that fixed charge. So if I just find the first one, so this is a potential energy at 0, 4. The potential energy due to this charge is Coulomb constant times its charge, which is 50 microcoulombs. And then the charge of the particle of whose potential energy we're finding, which is minus 15 microcoulombs. And then divided by the distance between them. This is a really quick Pythagorean theorem. It's 3 here and 4 here, so we have a distance of 5 meters. And then we're going to have to add the potential energy due to this particle. Of course, everything here is the same, though. It has the same charge and the same distance, so the potential energy will be the same. And notice here we don't have to worry about vectors at all, because this is a potential energy. So all we need to worry about is the absolute distance between them. There's no directions here to worry about. So actually, because the distances are the same and the charges are the same, the potential energy will be the exact same. So we're going to get a total of whatever it is from one of them times 2. And if you carry this out, you find that this works out to about minus 2.7 joules. And it's okay that it's negative. Certainly, it can be negative. Okay, so now we have a potential energy of this particle when it's at that point. It's at a potential energy of minus 2.7 joules. What is its total energy? Its total energy is the sum of its kinetic and its potential, which is minus 1.5 joules. Now, whatever its energy is at 0, 4 is the energy all the time. So we can just say that the total energy at any given time, we don't need to specify that it's a 0, 4, because that doesn't change, is minus 1.5 joules. Now, the second step is to use this value to find the kinetic energy once it's reached the origin. So what's changed at that point? At that point, we're going to have a different distance between that particle and the two fixed charges, so its potential energy will change. And therefore, because its total energy is the same, its kinetic has to change. So go ahead and do that on your own. Now find the potential energy when it's reached the origin, and using the total energy, subtract to find the kinetic energy. We'll come back and take a look and compare our answers. For the potential energy when it gets to the origin, we have a similar formula is up here, the Coulomb constant times the product of the charges, which are the same. But now the distance between the particle that is moving and the two particles providing the potential energy has changed. Now it's 3 meters for both as opposed to 5 meters. So I'm going to put 3 down here in the denominator. And again, because the potential energy provided by each one is the same, because they have the same charge and the same distance, we can just multiply this guy by 2. And if you carry that out, you'll find that that equals about minus 4.5 joules. And so finally, we can find the kinetic energy at the origin, which by just inverting this formula equals E minus U. E is the same because it's conserved. So it's minus 1.5 minus, the potential is minus 4.5, which gives 3 joules. Now earlier we had noted that because there's a net force in the downward direction, we expect the particle to speed up, and that means that its velocity should increase as it gets down to the origin. And that also means that because the velocity is increasing, its kinetic energy should increase. Is that what we found here? Yes, we found that the kinetic energy at the original point was 1.2 joules, and now it's increased to 3 joules, so the particle has indeed sped up. To find that velocity, you just use the fact that kinetic energy is 1/2 mv squared. And then using the mass that we have up here, which is 10 times 10 to the negative, it's 10 to the negative 10 kilograms. Solving that, you should find that the velocity of this particle when it gets to the origin is about 2.45 times 10 to the 5 meters per second. Right, so that's the answer to the problem. And I just want to point out here that notice that we were able to get velocities here without dealing with a lot of the complications of having to deal with the forces. And then once you get the force, you got to deal with the vectors. Then you got to take the acceleration using Newton's second law. And then you got to integrate to find the velocity. So whenever you can use energy, you can bypass a lot of that stuff. But you have to be very careful about applying this conservation of energy because in some cases, energy is not conserved. And you also have to think about all the sources of possible potential energy and kinetic energy. So when you can use it, it's very useful. Just be careful when you do so. Let's take a look at the summary. In this problem, we were asked to find the velocity of a particle moving under the influence of Coulomb forces. First, we determined the total energy of the particle at one point by adding the potential and kinetic portions. Then we found the kinetic energy at a different point using the conserved total energy and the new potential energy. Finally, we determined the velocity from the kinetic energy. This problem kind of suggested us to use energy considerations because we were told the kinetic energy at a certain point. But many problems may not tell you that explicitly. So as a general rule, you will find that you can use energy considerations when you're looking for velocities or if you have a velocity, and you're not dealing with accelerations. Notice here, nowhere in the kinetic energy formula is there an acceleration. So the price you pay for using energy considerations is you cannot find accelerations. When you are dealing with accelerations, the best way to approach that type of problem is to use forces and fields. But when you're dealing only with velocities, the best way to approach that type of problem is to use the potential energy and the electric potential. And so in cases where you're not given the energy outright, always try to analyze a problem and determine what you're looking for. And this method may be easier in some cases, whereas accelerations and forces and vectors may be a little easier in different cases. In any case, let me stop here. If you have any comments or questions regarding the video, please leave them on the link attached to the video, and we'll see you next time.